So my name's Dustin Kirkland. I work for a small startup in Austin, Texas called Gazang. I'll talk a little bit about them toward the end. But here I'm here to talk about reining in security sprawl. This talk is really directed at architects of solutions, developers of solutions that are probably built on top of any one of a number of Apache projects. I'll start out with just a bit of justification about this, and this is about compromises. I've been in the security track all morning. I listened to a couple of interesting presentations about CVEs and vulnerabilities in the software, and perhaps that's where some of these leaks come from. But from this perspective, I just want to look at some hard statistics this is from the U.S. Department of Health and Human Services. Over a 3-year period between 2009 and 2012, 21 million Americans' health records have been exposed. That's 21 million different people. That's over 6% of the United States. There were a total of 480 reported breaches, and out of those breaches, I did some analytics on the you can actually grab a CSV file of the data. Almost 72% of those compromises consisted of theft of physical media, lost devices, tapes, drives, or media, and improper disposal of that media. This is information that leaked out about people, real people, and it leaked because the media was not taken care of. At least that 72% is trivially solved by encryption of data at rest, and I'll talk about that in a second. The other 28%, there's a bunch of different problems that need to be solved. The Shiro talk a few minutes ago, I think, could address quite a bit of the rest of that in terms of protecting through authentication and authorization that data, at runtime. Looking at a different vertical, student records. This information came from privacyrights.org. 3 million students have had their student records compromised due to very similar attacks. The statistics were compiled in a slightly different manner, but what is important is that these are real people. The entire student body at University of North Florida, everyone's social security numbers were breached. The same thing at actually a Eugene, Oregon school district nearby. 16,000 social security numbers, birth dates, and student IDs were leaked. And this just goes on. All this fundamentally comes down to the fact that a paradigm is changing, is evolving. Specifically, security in the cloud is a very different landscape than our traditional behind the firewall style of computing. And I think this crowd, the Apache crowd, has as much appreciation for that as anyone. In the cloud, your security gets outsourced and distributed. Not just your computing resources, but your actual security. You give up some of the usual physical and logical barriers that protect your data. From a automation and orchestration perspective, cloud means you've got to automate things and that previously maybe were able to be handled manually. You could type a couple of passwords on the couple of machines when they needed to boot and mount an encrypted volume. When you're talking about cloud computing, you can't do that. You have to automate and orchestrate. That means quite a bit of non-interactive, non-password, and automating the authentication processes. From a numbers game perspective, there's just an exponential increase in the number of systems that are under management and the amount of data under management. And then finally, just a pet peeve of mine, the fact that there's really a lack of quality randomness in many cloud computing environments, a lack of entropy, and that can yield insecure key generation. I've got a whole nother presentation dedicated to entropy and ways to solve that in cloud computing. Come talk to me if you're interested in that, but that's just one small piece of this. So similar question, but what's different about security in big data environments? Cloud, big data, they kind of go hand in hand these days, but there are a couple of nuances with respect to security. First of all, big data is exploding. I mean, we're talking petabyte scale storage systems. That's just inconceivable a decade ago, and that's just kind of the ticket to ride now when it comes to a real big data deployment that someone's going to take seriously. But along with the data that's actually exploding and growing exponentially, so are the keys and certificates that are used to manage and protect that data. The other thing about big data is that there's often diverse projects and organizations. In many of the companies we deal with, there are multiple big data, so-called big data projects spread throughout an organization. You get into an organization that has 10,000 people or 100,000 or more. They may have a dozen big data projects and very different standards by which each of those projects are managed. And hence, and this is where I think hopefully we finally got into the premise of this presentation, the security itself sprawls out of control. Policies in place to guide that security of those projects often don't exist, and that can cause real problems managing that data, and that's often how these sorts of breaches happen. So what I have are a couple of case studies across several verticals, real customers of ours, and how we're helping them address that: healthcare, education, finance, SaaS vendors. First thing to understand is that the sensitive data itself is proliferating. There are more and more operating system environments out there. Each node or each instance, be it in an infrastructure as a service or a platform as a service environment, there are numerous private keys, configuration files, log files, application data, user data, passwords, machine data, just the DNA that makes a machine unique, makes that cloud instance. Once the cloud instance boots and takes on its own identity, what is that machine? That's the machine's DNA, and sometimes that information isn't necessarily a password or a certificate, but it is information that someone could use to clone that instance and perhaps launch a viable man-in-the-middle attack. So what can you do? And I'll go into each of these in great detail, but there's sort of four tenets that I tend to preach to our customers. One, always encrypt the local data at rest, and I'll show you some best practices how to do that. Always also encrypt the network data while it's in motion or in transit. You can do all the encryption in the world you want to do, but if you don't protect the keys and certificates that guard that encryption, you really haven't solved a problem yet. So you need to protect the keys and certificates appropriately. And then finally, monitoring, logging meticulously the network events and what's coming and going. So in terms of local data at rest, unfortunately, disks do disappear. That's how 72% of those 21 million healthcare records, just the disks disappeared, and that causes compromises. Some industries are required by law to encrypt data at rest. We see that quite a bit in health and finance and academia. Other industries are self-regulating. PCI, for instance, is a standards body that is run by the credit card agencies, and they require people who take Visas and MasterCards and American Express to abide by a certain set of policies, some of which include encrypting those credit card numbers if it ever gets stored on a disk. That's not regulated by the government. That's regulated by private industry because it's expensive when they have compromises. In any case, there's a number of verticals where this practice is actually required, and I think there are more and more that will be following suit. Encryption at rest can take a number of different forms. The two that I've mentioned here are at the file level and at the block level. I've mentioned here two file systems built into Linux. One's eCryptFS and the other is dmcrypt. Actually, dmcrypt is a block driver layer. eCryptFS it's a virtual file system. I'm actually one of the authors and maintainers of eCryptFS. And have been for some time. eCryptFS is a file system in the Linux kernel. It's a layered file system. You mount one directory on top of another directory, and you specify the passphrase and the salt and the initialization vector and so forth. But what you end up with is a mount point where there's an upper directory that is a decrypted view of those files. They don't actually exist in any decrypted view except in the kernel's memory, but applications can read and write data to those files as if they're real files. Like I said, that's just a representation of those files in memory. The way they actually exist are as encrypted data on the lower file system. I said there's two directories. You mount one on top of another. It's kind of like NFS. You mount this NFS, IP address mount point to another directory, and then you read and write data from that directory. But there's no files that actually live in that directory on the local system. eCryptFS works the exact same way. There's a lower directory and an upper directory. At the block level, Linux supports something called DMCrypt. DMCrypt stands for Device Mapper Encryption. With DMCrypt, you can actually encrypt entire block devices. That can be a disk, that can be a partition, that can be a volume if you're using LVM or something like that. DMCrypt and eCryptFS complement one another in what they do. They each solve problems at a different layer. DMCrypt at a much lower layer, closer to the hardware, and DMCrypt is quite a bit faster. With Intel's AES-NI acceleration built in some of the modern CPUs, DMCrypt can actually offload that AES the cryptographic operations to the coprocessor on the CPU and really accelerate how quickly that encryption and decryption's happening. But DMCrypt is a very blunt object. It's a very blunt tool compared to eCryptFS. With eCryptFS, you can be pretty surgical about you want to encrypt just this directory, or you want to encrypt just this file. You want to encrypt these files, but not these other files. You want to use one key for this file and a different key for this directory. DMCrypt is a single key for the entire mount point, and it's sort of all or nothing. You also have to set up DMCrypt at the time before you format the file system, right? So you set up DMCrypt on the volume, and then you format the file system, and then you've got a mount point that you can use. eCryptFS works on top of file systems such as ext or XFS or Btrfs or actually any of the Linux file systems it'll work with. What that means is that you can actually set up eCryptFS long after you formatted the file system. It's something that you can do on a running or legacy system, for instance, whereas DMCrypt, you need to provision the entire disk and decide to encrypt it at the time at which you initially format that file system. In either case, both of these tools are freely available in any Linux distribution since 2006 probably. Used at length in especially in appliances and in purpose-built systems. Every Google Chromebook that ships actually uses eCryptFS to encrypt what little local data is stored on the system, your browser cache and such. Every Google Chromebook that's ever shipped uses eCryptFS at that level. There are a couple of NAS, network attached storage manufacturer, Seagate is one of them, where they actually use eCryptFS embedded in the controller to encrypt the disk or encrypt the data as it's written to disk. DMCrypt as well you will find in a number of different places. Android smartphones, as of the ice cream sandwich release, has an encrypt this device option, which will actually allocate some space and encrypt that space using DMCrypt. So both of these technologies are used at scale, quite a bit on the consumer side, quite a bit on the enterprise side. And eCryptFS also is used by Ubuntu if you choose to encrypt your home directory. The one-click encrypt my home directory option. That's eCryptFS at work. The company I work for, Gazang, has actually built a wrapper for these two tools, a set of basically management utilities that can help set this up in a very consistent way across an enterprise, deploy that at scale, and interface with a enterprise key manager. We call that ZEncrypt, but it supports both eCryptFS and DMCrypt. It's essentially commercial support for these two encrypted file systems. From a performance perspective, if you're leveraging AES-NI for hardware acceleration, the performance is negligible. It's less than 1% impact on whatever your workload might be. If you don't use AES-NI, it's typically in the 3 to 5% range. It really depends on the workload and how fast the physical media is backing the file systems. The faster the media, the more you'll see the impact of encryption. The slower the media, the less you'll see the impact of encryption. Basically, the mathematical process of encrypting and decrypting data can usually fit within the I/O wait of fetching the next block from disk. When you have a really fast disk, an SSD or something like that, you're fetching the data as fast as you can actually fetch the data sometimes faster than the crypto, the math can happen. So the second part of this is encrypting the data in motion, network data. Particularly in Apache projects, most Apache products have native SSL or TLS support built into the server. You know, anything from HTTP to Hadoop or have SSL available within the source code. It's a matter of hooking a handful of functions, especially the network-facing functions, to be able to make the appropriate library calls to TLS or SSL. But actually in practice, and I do quite a bit of work in business and enterprise, it's actually pretty rare to see you know, especially Apache projects deployed with SSL enabled. It's there, but it's too often it's not even enabled. And there's a good reason for that, or there is a reason for that, and that's that the certificate management is actually really hard. It's hard to get right. You can do it a number of ways. The most expensive way is by buying a commercial CA signed certificate for everything. But you know, when we're talking about a massive you know, Hadoop cluster or something like that, that's just impractical. It doesn't scale. It doesn't scale very well. You can also use self-signed certificates, and you know, you can do it in an insecure way, which says, yeah, just ignore the certificate as long as I'm doing encryption. Sure, I'll take it. That's not good for obvious reasons. Man-in-the-middle attacks become very easy there if you ignore the certificate and you just say, sure, whatever certificate you have, I'm going to take that. That's the process you go through in your browser when you accept a, you know, this certificate doesn't look valid. Do you want this? If you just click accept, everything you're doing there is encrypted, but you don't know who you're encrypting this data to and from. You actually can do self-signed certificates and be secure. What you'd have to do, though, is pre-share your own certificate authority on each node at deployment. So you could add yourself to the root chain on those systems, but you'd need to put that into the etc SSL CA certificate cert at deployment time. And that can be done, and we've done this before using Puppet or Chef or, you know, whatever your orchestration mechanism is for provisioning systems. If you can you know, establish that early in the bring up of the cluster, it can be done, and you know, your systems will never get if you do it right, your systems will never get the invalid certificate type errors. What this all means is that effectively PKI is essential. It's essential to getting this right. It's hard to do, if not impossible to do, SSL and TLS without a PKI, a public key infrastructure. And finally, and this is, you know, back to the previous pet peeve, you have to make sure you have sufficient entropy to generate quality certificates. Without sufficient entropy, your certificates could be, you know, scarily similar to another certificate generated by another very similar virtual machine or node that could be reproduced at some time later by an attacker. So following on that, protecting the keys and certificates. There's two pieces of the PKI. One's the public piece, you know, how do you share public keys and sign public keys. What this slide is about is how to share or how to protect private keys and private certificates. And that's really at the heart of the root of trust. If you don't have sufficient protection on the private keys, you know, the integrity of that data is really not guaranteed. It's essential to store those keys separate from the encrypted data. Maybe that goes without saying, but it's very difficult to do in practice. That means you've got to have that, you've got to keep the key separate from your encrypted data, but you need to have access to the key at the time at which you need decrypted access to that data. And perhaps it's at mount time if you're mounting a file system, or at backup time if you're creating backups of you know, backup snapshots of a database or something like that. The best practice here is to always avoid storing those keys and certificates on the disk, and that's something that is really difficult to do in web servers where they need a private, you know, SSL. You know, mod SSL needs a private SSL certificate so that it can launch and load. So where do you put it? Well, you put it in etc SSL. If you're of the mindset you can password protect it, but that means an admin has to be ready to type that password every time you boot your Apache server. Maybe that works okay for your one server, but it sure doesn't work for a cluster of machines, and it certainly doesn't work if you need to maximize uptime. The other thing that happens from time to time is hard coding those within an application, writing a password or passphrase or private certificate directly into the app, and frankly that's no better than storing it on disk. So as I said, the best practice here is to retrieve those keys and certificates dynamically at the time of use, the TOU, and then discard them immediately, and make sure that you put them into secure memory, MLOC, and discard when done. What this means, though, is that you've got to institute the policies that guard the retrieval of those keys, okay? So, your policies would be what would guard those keys from being retrieved by your attacker, right? Your attacker wants to retrieve that key in the same manner that you retrieve the key, but the policy would need to distinguish between a legitimate request for the key and an illegitimate request. So once again, this is the other piece of what Gazang provides to our customers, and that's a product called ztrustee. It's a REST-based web service for key retrieval, authenticated key retrieval. There's a ztrustee server, and there are many ztrustee clients. The clients authenticate to the server and request keys by handle or universally unique identifiers. Each request for a key, or we call them opaque objects, deposits. It could be a key, it could be a file, it could be a directory, it could be gigabytes of data, it could be a short password or passphrase. It really doesn't matter. That's opaque to the ztrustee server. But what the client does is it authenticates to that server, and the server checks the authentication of that client. Are you a valid client? Do you have access to the key you're requesting? Are you expired? Is that deposit expired? Can you meet all the policies necessary to retrieve this? And the policies include a TTL on keys. Keys can expire after in seconds or days or weeks or months or years. Is the number of times that that deposit has been retrieved, is it below the retrieval limit? So you can have keys that are retrievable exactly once or twice or 3 times. Those are called nonces. So we can put a nonce on certain keys or certificates and rotate them accordingly. And then the most unique aspect of ztrustee is the trustee aspect. You can actually name trustees, which are either humans or processes, who guard the release of that key. And this is a person who has to sign off on the release of a key. And signing off could mean either clicking a yes or no in an encrypted signed email that the admin would get, and the server would put the client in a waiting poll until the trustee releases that key, or we've actually got mobile apps to do that as well. So and the trustee never actually has access to the key of their certificate or the private data. They only have the right and the responsibility to authorize the release of it. So this is the way to get around this is the secure solution, we believe, to the password protecting your SSL certificate in mod SSL at load time. So what you would set this up, and then your sysadmin, one or more sysadmins, you would name as trustees. You could name 5 admins as trustees and require that 2 out of the 5 or any number out of the 5 release that key or authorize the release of that key. And they never actually have access to the private certificate itself, but what they have is the ability to click authorize or go out of band and legitimize that request. And then the final piece of this advice from an architectural standpoint is to ensure that you're always monitoring and logging and doing that meticulously. Some services have native logging tools. Others, you may need third-party applications like a Splunk or something like that. Almost any application, especially the Apache applications, do a fabulous job of putting out quality exhaust, just application exhaust, and then being able to accumulate those into an appropriate data store and then analyze them appropriately. Analyzing them is essential. Auditing the logs, it only does so much good it does little to no good to have logs. You really have to be able to audit them. To do it live and in real time can really help thwart the worst live attacks, but even analytics after the fact can detect aberrations. It's nice to do that when you can do it in real time. There should be some checks in real time. Others are more post-mortem, knowing what's going on after the fact. So right now we're protecting customers running each of these Apache projects: Accumulo, Cassandra, Couch, Hadoop, and Friends, Tomcat, and Solar. as well as other non-Apache projects, ClusterFS, MongoDB, MySQL, Postgres, and React. We've got customers in production that have critical data, some healthcare, some finance, some student records, some not regulated data, but data that these customers feel a need to protect. And in all of these cases, the Gazang encryption and key management slide in underneath their data running in these applications, and the applications are essentially, it's transparent to them. They don't even need to know that there's encryption happening underneath. So a couple of case studies. One, and I'll leave you guessing who these companies are. One is a global mobile device company, cell phone manufacturer. They're streaming and storing user credential data from the handsets to their data center, their cloud, so to speak. Every single one of those, every object that they stream necessarily includes personally identifiable information about the person whose handset this is retrieving that information from. They use a suite of applications to analyze and operate on this data. In fact, it's quite a bit of Cassandra among others. To the user, this is a benefit of being able to back up and restore the device state at some point, to be able to replace the device and restore its state somewhere else. But they also run analytics to determine maps and traffic patterns and produce some targeted advertising. This company uses our software to protect all of the data at rest. It's Cassandra plus Hadoop, and this happens inside of their own data center. So there are similar protections that need to happen, whether it's a public cloud or a private cloud or a hybrid. In this case, this is an on-premises data center. At the very lowest level, there's encryption happening before this data goes to disk. There's a whole suite of access policies sitting on top of that. But what we can do is ensure that they meet their regulatory compliance to encrypt the PII information. In a second use case, there's a SaaS vendor, someone who is running an application in a public cloud, an Amazon cloud. They do identity management. They are what they found, what their internal processes found, was that they had this massive security sprawl without management or policy about the passwords and the operating system data in their cluster itself, and they really wanted to centralize the keys and certificates and the password and the management of that. They used us in their SaaS application, which is another Cassandra and Friends sort of application to encrypt that data in a public cloud. They're unique in that they're using the API directly, our Java API directly, to talk to the key manager. And that's, I think, a pretty interesting use case. And then finally, similar, to all three of these are similar in that they're protecting data at rest, but this one's a healthcare SaaS vendor. Patient records, literally patient records, demographic information, billing. They run analytics for physicians and health plan administrators. We help them meet their HIPAA and their PCI requirements by encrypting their data at rest and the key management. They're unique in that they've got a public-private hybrid model. They run some information in a public cloud, and other stuff they do behind their own firewall. From a compliance perspective, this is interesting in that they want to use the public cloud more because it's more economically feasible, but they couldn't do that before without encrypting that data, and that wasn't a solution that they had in place at the time. So encrypting their data enabled them to actually use a public cloud where they were previously not able to. So I just wanted to make a brief but public thank you to Apache for each of these projects. These are projects that we use and we depend on, that our customers use and depend on every day. I've met some of the developers around here. It's pretty cool. But Cassandra, of course, Commons, Hadoop, HTTP, Maven, Tiles were. I'm sure I missed some in here, but a quick grep of our infrastructure turned these up pretty easily. So we're headquartered in Austin, Texas, venture funded, encryption, key management, and we help our customers meet their compliance requirements. I maintain a number of open source projects, eCryptFS just being one of them, but fairly active in open source communities. I'm a little bit new to the Apache world, so I appreciate the open arms here. Yeah, I've been around Linux and open source for a long time. Any questions? Yes, sir.
How is the authentication performed against the key server?
Yeah, great question. So we use asymmetric encryption, actually GPG, GNU PG. Every message that's sent from a client to a server and a server to a client is signed and encrypted, and inside of that signed encrypted packet is a JSON data blob, key value pairs that the server uses to operate on or the client uses to operate on. That public key encryption, that asymmetric encryption, means that it's encrypted, which means no one else can read the data except for the intended recipient, and it's also signed so that the server knows who it's talking to and the client knows that only the server it sent it to could see that. Now there's a second piece to that, which is there's a sequence number, there's a rotating token that once the client and the server have established a trust, they each increment, they perform an increment type operations. It's actually a hash sequence. But if that ever gets out of sync, if someone were to grab the configuration data from a client and try to move it somewhere else, that would get out of sync immediately and the server would be able to cease communication. We also have a layer where clients can have their public keys signed and authorized by the server. And servers can be signed and authorized by clients, and we respect signatures on those keys. If a particular deposit requires a signed key, that signature can be enforced, and if that signature is ever revoked, the server will respect that. It's really built on top of the public key infrastructure. We have a side project for a replacement for essentially a new public key server. It's called Hockey Puck. That is an open source project that Gazang works on. We just released it earlier this year. Hockey Puck is a replacement for SKS, synchronizing key server, similar to like a pgp.mit.edu or any one of the public key servers. This one is a much faster asynchronous key server than the current implementations. That maybe was a little more than you were looking for. Did that answer your question?
Mostly, yeah.
Okay. What else?
So, where does the key come from that is used for that whole key?
And you still obviously need to store the PGP locally.
Yeah, so that is a piece of, we call it a session key, and that ultimately is stored locally. So that's yet another key to manage. From this perspective, it's a cookie. It expires. It doesn't last forever. You've got to re-authenticate. The sequence number tries to keep it in sync. Fundamentally, there's something that you've got to have that identifies you, and the goal is to store the big secrets, the permanent ones, the long-term ones on the server, and then authenticate and retrieve them, use them, and discard them when possible. That's the best I can tell you. Thanks. Any other questions? Okay, all right. Maybe we ended a little early. Okay. Thanks.